Davisson and Germer experiment. The Davisson-Germer experiment, conducted in 1927 by Clinton Davisson and Lester Germer, was a groundbreaking experiment that confirmed the wave nature of electrons, supporting Louis de Broglie's hypothesis of matter wave. They demonstrated that electron beams are diffracted when they fall on crystalline solids. The experimental setup. Here you have a filament and an aluminum cylinder with a fine hole. These two are connected by a potential difference V, the cathode and an anode. Here you have a nickel crystal and these lines represents the lattice plane. The electron beam hits the nickel crystal and get scattered in a particular angle. And the scattered beam is detected by using a detector, and this detector can be rotated through 360-degree angle. Electron source. A heated filament emitted electrons that were accelerating using potential difference. Nickel target. The electrons were directed at a crystalline nickel target. The surface was carefully prepared to ensure its regular atomic structure. Detector. A detector was placed to measure the intensity of the scattered electron as a function of angle. Key observations. The potential is kept at a constant value of 54 volt. At an angle of 50 degree, the intensity of the scattered beam is maximum. At a specific accelerating voltage 54 volt, a peak in intensity was observed at a scattering angle of 50 degree. This peak was due to the constructive interference of electron waves scattered by the atomic plane of the nickel crystal. By Bragg's law, 2d sin theta prime equals n lambda. D is the lattice space and theta prime is the glancing angle and n is the order, lambda is the wavelength. Good. Now, the theta here represents the scattering angle, whereas the theta prime is the glancing angle. Let us extend the lattice plane and we find the angle theta prime equal to 65 degree and the gap between the lattice plane D equals 0.91 Armstrong. Substituting this value, 2 multiply 0.91 multiply 10 power minus 10 multiply sin 65 equals 1 times lambda. Simplifying, we get lambda equals 1.65 Armstrong. So the experimental value is lambda equals 1.65 Armstrong. Theory. At an accelerating voltage 54 volt and at a scattering angle of 50 degree, we find a peak in intensity of the scattered electron beam. At a potential of 54 volt, let us take the angle at x-axis and on y-axis, let us consider the intensity of the diffracted electron beam. We get a curve and the peak in the curve is at an angle of 50 degree. Good. By de Broglie wavelength, lambda equals 12.27 over root V Armstrong. Let us substitute V as 54 volt and simplifying, we get lambda equals 1.67 Armstrong. So the theoretical value is lambda equals 1.67 Armstrong. Significance. Confirmation of matter waves. The wavelength calculated from the diffraction pattern matched the de Broglie wavelength, verifying the wave nature of electrons. The Davisson-Germer experiment bridged classical and quantum physics, making a pivotal moment in modern physics.